begin, we launch the Hammer Impact software, which we can find from the Applications side panel in DATS. The screen we're presented with is our test information screen, where we set various parameters about the test we're about to perform. I'm going to begin by selecting a results folder, which will be a folder where all my data will be saved. And I'm going to create a new folder on my desktop and call it Hammer Impact Test. Additionally, we can set a test control file, which is the information shown on this dialog. It will be saved in a test control file. We could save these and use them again in a future test, but in this case I don't have one that I've created earlier, so I'm going to save the setup as well, and I'll save that on the desktop in the Hammer Impact Test folder, and I'll call it Setup. So now you can see I have my setup file and a results folder, and I can also set a test description. And I now have to set up the type of test. We have the choice between roving excitation and roving response. In this case we're going to have a roving excitation. I'll be using a single channel force instrumented hammer and a single channel uniaxial accelerometer, and that will be in the roving excitation mode. The accelerometer will be fixed and the hammer will be moving from node to node. The number of components I have in this particular example will be 1, that is, there is one part to my structure, and my response directions will actually be 1 in this case because I'm using a uniaxial accelerometer. So I'm going to enter a component name. In this case it's a beam, and I'm going to have 22 nodes, and I'm going to attach the accelerometer to position 22. So at the end, and I have the possibility to enter the impact direction and the response direction. And I can also select which nodes are impact positions. In the case of this example, all 22 are impact positions. I can choose to save the FRFs only, the FRF and the coherence, or the FRF, the coherence and the time series of the impacts and responses. And I can select whether or not I would like to use response windowing and excitation windowing. The P8000 that I have connected has yet to be detected, as shown by the no hardware label here. If I click on the flashing button, detect P8000, we'll see that it will pick up the P8000, and I just simply have to select which channels are my excitation channels and which channels are my response channels, and which node is connected to which response. In this case it's very simple. I have only one excitation, which is channel 1, and I have only one response, which is channel 2, and as I've already specified in the component and node information above, that's connected to node 22 on my beam component, and it is in the +x direction. I can set the units, which are meters per second squared and newtons, and I can set the sensitivities for my sensors. They are both IEP type sensors. For the impact hammer it's 2.25 millivolts per newton, and for the accelerometer 1.04 in this particular case. So if I would like to have the setup checked for me, I have the check setup option, which will check and make sure I've set up everything correctly. And there is also the auto setup option. You can select the number of accelerometers that you have, and I could have used the auto setup option and it would have filled in this information for me automatically. Next we'll move on to the test setup. So next we begin the test setup, and here we can set various parameters about the test, including the analysis frequency, the frequency resolution, the number of averages, the pre-trigger, and we can also calculate the best trigger level for us to use for our force, and the response and excitation windowing if we had selected those to be used, which we did for this particular case. So to begin, I click the flashing green Start Pretest button, and then I just make several impacts on the structure in various positions. And what we'll see is the software has calculated for us a value of just under 17 newtons, and now the window test start light is flashing, so we'll start the window test. And this will require just one impact somewhere on the structure. And what we see here is the response signal, and overlaid across the top you can see the window which has been applied to that particular response signal, with the transfer function and a modulus and phase display. And we can see the value here of the attenuation has been calculated and the correct exponential window to achieve our goal. So we'll stop the window test and start the excitation window test. We have the option to set the transition start point and the transition length as percentages. We'll leave those at the default 10%, and again we'll make one impact. And we can see our excitation signal, and we can see the windowing that's being applied to the excitation signal and the frequency spectra. So I'll stop the window test, and now we'll move on to the data capture stage. And the data capture screen shows us the entire project. We can see the 22 nodes, the impact direction to remind us which direction to make the impact. And again, we can see we have the simple start button flashing green ready for us. We'll click the start button, and the first node is ready for us, so I'll make my first impact. And we can see our force signal, our response signal, and a transfer function. I'll continue with the second impact, and finally with the third impact. We asked for 3 averages for this particular test, so now we can see a coherence and the transfer function. And you can see we're ready to move on to the second node. And we're just coming to the end of the test now with the final 2 nodes. And we can see on the screen the transfer functions with phase. After we've completed 2 impacts, you'll see the coherence appear at the bottom of the screen. That's because you need at least 2 transfer functions before you can calculate coherence. And the final node, where our accelerometer is attached, and we can see now we've completed the test. The status shows a green tick for every node. It's possible for us to jump back and do any node if we'd like to redo it, and we can also use this undo last node button to remove the last impact. We can see the average here is a count of 3, but if we're happy we can just click on the stop button, and we have to confirm that we would like to stop the hammer test. Had we wished to stop the test halfway through, it's perfectly possible to end the test halfway through and then to return to the same test later. But now we've completed the data capture, we will look at the results and reports section next. The results and report section shows us the transfer function with phase of each and every node in this particular test. We can scroll through them one by one. It's possible to view them in both linear and in logarithmic. it's possible for us to use cursors and to read values. Additionally, it's possible for us to select a band and have a damping factor and frequency calculated for us. Additionally, apart from just being able to check each node, we can select one of these three options: show the individual node FRFs, which we're currently viewing, show component FRFs, or show structure FRF. If we select the show component FRFs, we are looking at the FRFs of each component, and in this particular test we had only one component, the beam. If we'd had multiple components, the show structural FRF would have shown us the structural FRF for the entire structure. So if we were to look at node 12, for example, in the middle we can see various peaks, nodes and antinodes, and we have the possibility to create a Microsoft Intaglio report of this particular node, which we'll see created for us automatically. But additionally, we can also look to an automated peak picking. So here we have all of the peaks chosen for us automatically. We can view that in linear or in log, and we can change the parameters, for example. So we only pick out peaks above a certain value. We can choose a frequency start and end range, and we can choose a maximum number of peaks. In this case, with the values I've collected, there are 4. I could refine that slightly to perhaps ignoring everything below 20, and we now have 5 peaks. And it's possible to create an Excel report of this information just by clicking on the Excel button. And additionally, it would be possible to make another report, an Intaglio Word report, showing these peaks using the Intaglio button once again. So taking a look inside our hammer test folder we created previously, we can see we have the Excel file which we just created. And we have our original report. This is showing the peaks, the position of the peaks, and a table of information about the peaks. And the first report we created, which is just showing the FRF for that particular node, it could have been a component or the structure. And then finally we have the data saved, which we can analyze inside DATS should we need to at a later date. And the data is stored in complex form, but here we can see all of the nodes. We selected in this tutorial only to store the FRFs. We didn't store the coherence or the time series, but it would have been possible to store those as well, and they'd be stored in different files.